In this video, we're going to answer the question, when is a line integral of a vector field independent of the path C chosen? Before we do that, let's back up a second and review the fundamental theorem of calculus. If we want to integrate a function f of t dt from a to b, we find an antiderivative of f of t, called capital F of t, and take the difference of capital F of t evaluated on the endpoints a and b. We can also replace little f of t with capital F prime of t. This is super useful because to compute the integral of a derivative, we instead compute the endpoints of the original function, which is way easier. Keep this in mind as we move through all the remaining sections. So now we're looking at line integrals of vector fields. We already know of a vector field that acts like a derivative, the gradient. The gradient of a function f of x, y, z is a vector made of the partial derivatives of x, y, and z. It turns out that for line integrals of gradient functions, we have a similar result called the fundamental theorem of line integrals. Said precisely, let C be a smooth curve given by the parameterization r of t, where t runs from a to b. Let f be a differentiable function of 2 or 3 variables whose gradient is continuous on C. The line integral along C of the gradient of f will be f of r of b minus f of r of a. In other words, the difference of the function values on the endpoints of the curve C. Notice that this means that we can compute the line integral of a gradient if we only know the endpoints of the curve C. For example, suppose f of xy equals x squared plus 2y squared, and r of t is the curve shown here connecting minus 1, 1 to 2, 3. To compute the line integral of the gradient of f along C, we can just plug in the endpoints into f to evaluate this. We get f of 2, 3 minus f of negative 1, 1, which equals 4 plus 18 minus 3, which equals 19. Notice that having the correct direction is important. If I wanted to travel from 2, 3 to negative 1, 1, then the line integral would be f of negative 1, 1 minus f of 2, 3, which equals negative 19. So what about general vector fields? For example, if we want to compute the line integral of f dotted with dr, where f equals y, x, and the curve C is given by parameterization r of t equals t cubed plus 1, t squared plus 5 for t from 0 to 1. You may think that you'd have to set up a long calculation for this, but let's think for a second. Is f equal to the gradient of some scalar function? If you stare at it for a second, you should realize that yes, if f equals x times y, then the gradient is y, x, which is exactly the same as the vector function f. This is great because then our line integral is just computed as f of r of 1 minus f of r of 0, which equals f of 2, 6 minus f of 1, 5, which equals 2 times 6 minus 1 times 5, which equals 7. Easy. Recall that we had a name for these kinds of vector fields. F is the conservative vector field if we can find a function little f where the gradient of little f equals big F. Little f is called the potential function for big F. So line integrals of conservative vector fields are easy to compute. Moreover, we can see that the path chosen between two endpoints doesn't affect the final answer. So line integrals of conservative vector fields do not depend on the path C, they only depend on the endpoints. We have a name for this too. If capital F is a continuous vector field with domain D, we say that f is independent of path if the line integral along C1 of f is equal to the line integral along C2 of f for any paths C1 and C2 in D with the same initial and terminal points. Thanks to the fundamental theorem of line integrals, we know that conservative vector fields are path independent. A couple questions now arise. Is the other way around true? That is, are all path independent vector fields conservative? Secondly, how can we tell if a random vector field is conservative? I'll answer these questions in a second, but let me include another viewpoint for this process. Let's suppose our curve C is a closed path. It starts and ends at the same point. For example, a full circle is a closed path. This triangle is a closed path, and so is this figure 8. What would happen if we compute the line integral of the gradient of f for a closed path C? Well, the fundamental theorem of line integrals says that you compute f of b minus f of a, where b and a are the endpoints of C. But in this case, the endpoints of C are the same, so f of b minus f of a would equal 0. This means that the line integral is 0. This property, along with the previous two properties, gives us 3 equivalent properties for a vector field. Let D be an open connected region. A vector field f is conservative on D, in other words, it's the gradient vector for a function f, if and only if capital F is path independent on D, and if and only if the line integral of f along every closed path in D is equal to 0. So it seems like being a conservative vector field is a very nice property. Now more questions. How do we test if a vector field is conservative? And if it is, how do we find the potential function f? We'll restrict ourselves to 2D vector fields in this video. In future videos, we'll attack the 3D case. Let's think. Suppose our vector field is equal to the functions p of xy, q of xy, and suppose f is a conservative vector field. Then this means that there is some potential function, little f, where the gradient of little f is big F. That means that p is equal to the partial derivative of f with respect to x, and q is the partial derivative of f with respect to y. Well, what would happen if we took the derivative of p with respect to y and the derivative of q with respect to x? P sub y equals f of x of y, and q sub x equals f of y of x. These are the mixed partials of f, and what we learned is that usually they're the same. So the partial derivative of p with respect to y would equal the partial derivative of q with respect to x. This gives us a necessary condition for conservative vector fields. If f equals p, q is a conservative vector field where p and q have continuous first-order partial derivatives on a domain D, then throughout D we must have that the partial derivative of p with respect to y must equal the partial derivative of q with respect to x. What this means is that if the partials of q and p are not equal, then f must not be a conservative vector field. For example, if f equals 3x plus y, 2y squared, then p equals 3x plus y and q equals 2y squared. If we compute their partials, we get that the partial derivative of p with respect to y is 1, and the partial derivative of q with respect to x is 0. Since 1 does not equal 0, f is not a conservative vector field. You may be wondering, what about the other way around? If the partials are the same, does this imply that f is conservative? With a little extra added to the hypothesis, this is true. What we need is for the domain to be simply connected. That means it's connected with no holes. This is a simply connected region. The whole xy plane is also simply connected. An example of a non-simply connected region is here. There's a hole in it. With this, we can state a converse to the previous result. Suppose f equals p, q is a vector field on a simply connected region D. Suppose that p and q have continuous first-order partials, and the derivative of p with respect to y equals the derivative of q with respect to x throughout D. Then f is conservative. Let's do an example. Suppose f equals 2xy, x squared plus 3y squared. Notice that the domain of f is all of R2, which is simply connected. So we can test the partials. The partial derivative of p with respect to y is 2x. The partial derivative of q with respect to x is 2x plus 0, which equals 2x. So these are the same. Thus, f must be conservative. So let's try to find little f. The gradient of little f is big F. So this means that the partial derivative of f with respect to x is p, and the partial derivative of f with respect to y is q. Let's focus on f sub x, which equals 2xy. To get to f, we need to integrate this with respect to x. We get x squared times y plus a constant. But when taking partial derivatives with respect to x, anything with just y is considered constant. So our constant in this case is some unknown function in y called g of y. So now we have to solve for g of y. We can use q to find this. Q equals the partial derivative of f with respect to y, which equals x squared plus 3y squared, which would also equal the partial derivative of x squared times y plus g of y with respect to y. This becomes x squared plus g prime of y. Solving for g prime of y, we get that it equals 3y squared. Now we integrate 3y squared with respect to y, getting g of y must equal y cubed plus c. This is an actual constant c, since we already solved for both variables. So putting this together, our potential function is f equals x squared times y plus y cubed plus c. We can also check. The gradient of f is 2xy, x squared plus 3y squared, which is exactly big F.